God. Okay, so as you can see that we are now moving forward into doing the calculations and looking at the formulas that relate to the gas law. So last time we covered last time we already covered the kinetic molecular theory, so which comes at the back of this chapter, but it's important to understand, you know, what gases are basically. Only then you can understand the gas laws. So we covered that. And important things, as I mentioned, is you need to make a note of these different conversion units. We will cover today the Boyles law, Charles law, Gay-Lussac, combined, and Avogadro, ideal, and STP, and Daltons. I hope I can finish this real fast. I'm hoping that you guys have done this earlier. So, you know, it is just going to be brushing up your memory. And so this is what we will do today. Next thing, you need to make note of these because these will be covered. Now, since you have a holiday on November, right? November the 11th. So obviously you're not coming to the class and it's a holiday. And so I cannot, you know, I cannot just keep on. We don't have much time left also. So what I'm going to do is whatever I can finish today, great. Otherwise I will be making a video of the remaining parts and put them on the YouTube, you know, or videos. You guys will have to cover that from there. So don't forget that, okay? So the other piece that you're going to leave here, so you are leaving these 9.2, 9.3, 9.4, because these are all calculations using these equipments. But there's another last piece that we are also going to leave is the kinetic molecular theory we already covered, non-ideal gas behavior. Okay, we already talked about the ideal gases. So you have an idea of what the ideal gases are. Basically, ideal gases don't even exist on this earth. Ideal gases obey all the gas laws. Ideal gases do not go any change of phase. So that is why, you know, they don't exist. On this earth, matter will undergo change of phase anytime there is a change in temperature or pressure. So with that said, the gases we have are real gases. They will follow the gas laws to some extent. After that, they begin to deviate. Whereas the ideal gases will continue to obey the gas laws till eternity. So that's, you know, not the reality of this earth. So anyway, so with that said, you are going to leave section 9.6. Okay, so leave it. So just to read it if you want, and if you don't want to read, don't worry about it. But let's get started now with the part one, which is Boyle's law. Okay, I don't know, since you guys have, that's the thing. So I think I should do these like the way we do it in the labs, because you guys didn't do the labs in your previous, you know, because of the pandemic. It is understandable. So you see, you should look at first how these gas laws came about. How were they discovered? So first is the Boyle's law. Okay, so here's the thing. These gases, the way we obtain them is we you know, basically, how do you get these gases? So first of all, how you get them. So here is this reaction going on in a test tube. Okay, in a test tube, and we have this, there's a one hold, you know, stopper. You, through the one hold stopper, you take this a thing that connects, like a connector, okay, that connects these this one end, and here is going to, you're going to collect the gases. And for the most part, these gases are collected in the like by the downward displacement of water. And you are already doing the lab. You have already done the lab, and some students will be doing the lab today. So you will understand like how these gases are collected. So this is a container, a trough or a beaker or something, and this is on a small scale. So you will see in the lab that you took magnesium. And so for example, in this case, let us say potassium chlorate. You heat potassium chlorate, it becomes potassium chloride, and it releases oxygen gas. Okay, now this oxygen gas is, so this is all water here, this is all water, and this is also water. Okay, this is also water. So, and let's say here is, we kept this is the potassium chlorate, and this potassium chlorate is actually now heated. So this is heating process happening here. And you can control the heat, you can measure the heat and so forth. So once the oxygen begins to evolve, this oxygen as a gas goes through this open-ended connector, and it goes all the way to this side where, because it's water, right? It needs some space. So gases starts moving up and you will see bubbles. And you are actually done the reaction with magnesium and HCl, and you've evolved, hydrogen is evolved, and you've seen the bubbles coming out from there. So here, same thing. As the gas moves, it begins to collect in this container, and the level of the water comes down. The level of the water comes down and it gets collected in this container. And slowly you will have this container containing a lot of, oxygen gas. Yes, it is going to be wet. It will be wet, a little bit wet, because it's coming through the downward displacement. Displacement is displacement of water. So that's the name of the technique, displacement of water. Okay. And this gas then is this, obviously it's removed, and then all this will have like the gas particles, all this is filled with gas. So oxygen released here as a gas gets collected, and fine, it has some oxygen, will have some water vapors in it, but eventually they are just cleared or dried or so forth. So we will see bubbles here moving up. So this bubbling is of oxygen gas. Okay, so this is the way we collect them. Now, after that, this is in a container. But then after that, what happens? They get transferred into these cylinders. And these cylinders contain these gases under very high pressure, because these are made up of metal. So these are basically iron, or even steel, made of steel or iron. And then they are sealed, they're like closed here, and there is a regulator here. So what does the regulator do? This regulator, it reads the pressure. Okay, it reads the pressure of the gas. Remember, what is a gas? Pressure. Pressure of the gas is these gas particles that are inside a container don't like to be compressed. They're basically compressed. They don't like to be compressed. They like to expand. They're looking a way out. That is why it's a steel container. Steel containers, they can't go out. So then how do we get the gas out from here? So remember, there is this little knob. This little knob, releases the gas. And we have a little, like a tube, plastic rubber tube with a little pinch here, which can like be closed and opened. So through this tube, so you open the knob, the regulator reading begins to change. It tells you the gas pressure is changing because now the gas is being released. So the gases come out from this tube, into something where you collect them. So in this case, we are collecting gases in a syringe. So here is a syringe, and you have a gas collected in the syringe up to a certain level. Okay, remember the syringes have a piston. You can move the piston up and down, and these syringes have marking, so that give you they give you like the volume of the gas. Okay, and then you seal the syringe also. So this is the syringes, are used in the lab to work with the gases, and these syringes are plastic syringes, or sometimes glass syringes are also used. Okay, so then now what we are doing, now we are looking at, once we have the gas in our hand, then now we are going to look at Boyle's law. So Boyles collected these gases in the syringe, and he studied the relationship of pressure and volume. Okay, volume is the amount of space the gas is occupying, and pressure is the pressure. Okay, and he kept the temperature constant. Temperature constant means that it is not changing, generally, at room temperature, and the room temperature is 26 degrees Celsius. Okay, generally 25, 26 degrees Celsius, maybe 27 some places, but generally that's what it is. Okay, so now we have, this is the syringe, and here is the gas sealed. So it's inverted, right? And what happens is, okay, in this case, here is a little regulator that reads the pressure, here. Okay, so in this case, in the side, you can put these special type of syringes. So here is the regulator to read the pressure, reads the pressure. And generally pressure is in ATM reading. Okay, now you have some amount of gas here, right? Some amount of gas is here. Note that initial pressure. Initial pressure is generally the room temperature pressure. So it's like ATM, 1 ATM. So pressure 1 is the 1 ATM. So 1 ATM. At 1 ATM, or whatever the pressure is, not 1 ATM, sorry, whatever the pressure is of the gas when there is a certain volume, 1, 2, 3, 4, 5, 6, 7, like that. So whatever the pressure reading is in ATM, note down the volume at that time, and that generally our readings are in milliliters, because our syringes and our equipments are in milliliters, but you have to convert that to liters. So milliliters is converted to liters using 1 liter over 1000 milliliters as a conversion factor. Okay. Next is, now comes a question, how are you going to put the pressure? Pressure is obviously, in normal life, we press the syringe with our thumb, but that's not the way to measure the pressure, right? We quantify it. So what we do is we put some weights, some weights, and this could be lead pallets or something. You put one weight. What happens is the piston moves down, and the pressure reading, this reads the pressure, it changes. So reads pressure, it changes. So note that down now. So we have the volume 1 we started with, and now we have, when we increased the pressure, that's pressure 2, whatever the pressure 2 is, you read the volume 2, what happens to the volume. So basically you are increasing the pressure, and now you put another weight, and we see again the piston moves down and the regulator moves some way, some direction. The regulator reading moves. There's a needle here. So every time a pressure is increased, we see the volume is decreasing. Pressure is increasing, volume decreases, and a time comes when you can't push it anymore. Either the gas converts to solid, that is sublimate, gas converts to solid, like in carbon dioxide, or the gas can convert to a liquid, like it can condense, condensation can happen, or the gas can also, remain unchanged, but maxes out. You can move any further. So maxes out, and you cannot move, you cannot push it any further. Okay, so we got a certain data here. So we have the pressure in ATM, and we have the volume in liters. So volume in liters always, and pressure in ATM. So when you put a graph, you see that as the pressure increases, the volume decreases. As the pressure increases, the volume decreases. The volume keeps decreasing, and a time comes when it becomes stable. No matter how much of the pressure you increase, the volume will not change. So that's how the graph looks like now. So this is the pressure volume relationship, where pressure increases, volume decreases. Okay, when the pressure is removed, or then the volume increases, because gases like to expand. So gases push the pistons, and so that volume will increase. So the relationship is expressed in the formula P1V1 is equal to P2V2. Okay, now here we will see the, let's see, so this is another situation where this same graph because, you know, graphs, we like to have a linear relationship. So what we have done is we bring volume here, volume in liters, and 1 over P inverse. That's for the pressure. And in that case, the volume is a straight line. Then it can be seen as a straight line. So the relationship between the pressure and volume is still, it is inverse relationship. Inverse
Record, please.
relationship. Inverse relationship means one goes up, the other goes down. Okay. Now, the real value of the Boyle's law is the applications of the Boyle's law. Applications of Boyle's law are in your own body. Applications of Boyle's law. You see this, that the lungs are, you know, here are the lungs. The lungs are surrounded by a diaphragm, right? This is, I mean, I'm just making them like, I don't know. The lungs are these are the lungs, and lungs are, you know, enclosed by a diaphragm, are enclosed in a diaphragm, in other words. So this is like a rib cage, right? So this is the diaphragm. Now, when you PHRAGM, okay. Now, you can do this also. You can do this, breathe in and breathe out. Breathe out. You can see that when you breathe in, what happens? When the air goes in, obviously the lungs are going to expand, right? So lungs expand when, you know, so why would the lungs expand? The volume of the lungs increase because the diaphragm, the outside diaphragm is representing the pressure from outside. So when you're relaxed, you can see that your diaphragm doesn't put any pressure. So when you're breathing out, when you breathe in, that means the diaphragm is less pressure, the volume is more. So diaphragm is not putting any pressure on the lungs. So less pressure, that's why the lungs get filled with air. But now you try to breathe out. Breathe out means you are pushing the air out. And in order to pushing the air out, and in order to do that, what do? The diaphragm puts the pressure. Diaphragm, DIAPHRAGM. The diaphragm pushes the lungs. So outside pressure has increased, the volume of the lungs decreases. So that is your applications of Boyle's law. Okay, breathing in and out. You try this, try it. I would just put it here. You try it and you will get a feel for it. Okay, you will get a feel for it. When the diaphragm is relaxed, then the lungs are full. But when the diaphragm is pushing, then you're releasing the air outside, the volume of the lungs is coming down. Okay, now let's do these problems. Check your learning problem. Okay. What is that about? The sample gas in 9.13 has a volume and pressure. Determine the volume of the gas at a pressure of P. Okay, let's do this. Learning problem, learning check. Or okay, learning check is 9.8. 9.8. All right, so here, check your learning. A sample of a gas in figure 9.13. So figure 9.13 is, okay, some gas in the figure, same thing we have drawn here, is a sample of a gas has a volume. So we are given the volume is equal to 30.0 milliliters, okay? And the pressure is 6.5 psi. Determine the volume of a gas. So what is the volume of this gas? So this is V1 and P1, V2. So determine the volume of the gas in 11.0 psi. Okay. You can use a graph to do that, So here you have the pressure in psi and the volume. They haven't changed the volume in milliliters. So you can do that using the graph. That's very easy. Or 1 over V graph, so you'll have to do this 1 over V, that thing, or just use the Boyle's law equation. So I'm going to just show the Boyle's law equation. P1 V1 is equal to P2 V2. Okay, now, since we are finding the V2, so we need to bring the P2 on one side. So P1 V1 over P2 is equal to P2 over P2 times V2. So this cancels out the P2 from this side, and you get the P2 on the other side. So that's the algebraic conversion. The rest is V2 is equal to P1 V1 over P2. Now, I am not sure. They have not changed the volume like they want. They have not changed the volume to milliliter, but they should, So it's okay. Let's just keep it in milliliter, see we get the answer. And if not, then we will have to convert to liter. So here is your pressure, 6.5 psi times the volume 1 is 30.0 milliliter over 11.0 psi. Now you guys tell me, what do you get here? 6.5 times, so you take this, psi and psi cancel out, right? And so now you do this, 6.5 times 30.0 divide by 11.0, and you get 17. So V2 is equal to 17.72. And is that what you, 17.7 milliliters? Yeah. So from the graph also, but by the calculation, yeah, this is the calculation, and calculation is more accurate. Okay, so this is the answer. So always, so for these, so some of you guys are making this mistake, and I'm putting this here. I'm going to write down here. Please note, always, oh, sorry. Please note, and some of you actually got better, so I'm happy with that. Please note, always write units, symbols, names, formula after the numbers. So this is one thing you have to do. Second thing is, for the gas laws, always write the formula that is the gas laws formula. Gas laws formula that you have to write, and show transformation. Show like transformation. How did you, do the conversion? How did you do the conversion? Algebraic conversion. Algebraic. So at least show some steps, if not all, okay, on the exam. So this is very important. So on the test, I'm just letting this to you, okay. All right, so please notice, don't forget that. All right, now let's look at the next one, which is the Charles law. Charles law is, this is the first one. That's the second is, second Charles. Now, Charles studied the behavior of gases with respect to volume and temperature, keeping the pressure constant. Okay, keeping the pressure constant. So how was this done? So what was the apparatus look like? So here is the syringe, same story. Here is the syringe, and there is inside the gas is filled inside the syringe. Okay, and the mouth of the syringe is obviously closed and is closed here. And the syringe, it has some gas filled in. So that is obviously going to be the volume. Now, this is filled. This is kept in the baths. These are called the hot and cooling baths. So hot baths means the temperature increases and you can increase the temperature till whatever, or there is a cooling bath. So cooling baths are when you need to take the readings at a lower temperature. So basically you can transfer this into, let's just get this. Okay, so here the same thing. Yeah, okay, so let's put this a hot bath in one place and then a cool bath. So this is hot bath, and things can be done at the room temperature also, and this is the cool bath. So hot bath is you can increase the temperature and then you can see at what happens to the gas when you increase the temperature, and then you can decrease the temperature also and see the behavior of the gas at that. So this way you have several readings. So this is hot and this guy is cold. And yes, there is going to be a thermometer here. You need a thermometer, and the thermometer reading, you can tell, even though it's outside, it's still like you can still tell the gas inside, how it behaves. So here is the gas inside and here's the gas inside. So as you increase the temperature, as the temperature increases, what happens? The collisions, as the temperature increases, the kinetic energy of the particles increase, the collisions increase. Okay, the collisions increase. And when the collisions increase, what happens? The pressure also increases and the piston moves up. Piston moves up, or the gas particles, they push the piston. Okay, so basically, I'll put this here, but that's better, that the gas particles, they push the piston up. And when that happens, what happens? The volume increases. So we see that there is a direct relationship of volume and temperature. When the temperature increases, the volume increases. On the other hand, when the temperature goes down, now you have cooled it. So here the piston was moving up and up and up. So, a time comes. That is why these are limitations. A time comes, if you keep on heating, there's going to be eventually explosion. So regardless, you will then have all these readings, V1. When the volume is 1, when the temperature is 1, the reading is 1. When the volume is 2, sorry, in other words, put it the other way around. When the temperature is 1, the volume is 1. When the temperature is 2, the volume is 2. When the temperature is 3, the volume is 3. So you can do it at different intervals. Now, when you cool it, what happens? Yes, the gas particles are going to, the kinetic energy is going to come down. So kinetic energy goes down, less collisions. So that means that the particles are a little bit more like stable. So pressure also decreases. Okay, so in other words, the volume also comes down. So here we see that the volume is directly related to the temperature, but as the temperature goes down, the volume goes down. And you have all these readings, at different temperatures, readings. So let's put this here, T4, V4, T5, V5, and so forth. Okay, so maybe I forgot to put one thing here. This is inverse relationship here. Pressure is inversely related to volume. Inverse. And inverse means like one increases, the other decreases. So inverse relationship. Okay. All right. Next is, we see this now, the Charles law. In this case, you have now a scenario where, keep this in mind, that ideally, volume should always be in liters. Okay. Temperature has to be in Kelvin always. And so when temperature is in Kelvin, we take the readings, thermometer readings in Celsius, U plus 273.15, and that will give you the reading in Kelvin. So always do this conversion. Volume, as we talked about, milliliters. If the question is specifically asking the volume in liters, so you are going to multiply it by 1 liter over 1000 milliliters. Yeah, and that will convert milliliters to liters. Okay, so now we have here what? In this case, let's see, the Charles law. So we have volume here, volume in liters, and temperature in Kelvin. Okay, so as the temperature is increasing, the volume is increasing. And yeah, there is, after some time, it is going to max out, either it's going to explode or whatever happens. But it helps, these graphs help us to find like some of the unknown values. So if we want to find out what would be the volume at a certain pressure, at a certain temperature, then you can just use that as a graph. But you can also use the formula. So before we do that, look at the applications of this. So let's write the formula first. The formula is, here is the formula is V1 over T1 is equal to V2 over T2. Okay, so these formulas, like I said, each and every formulas are all scattered. So I put them all in the handout also, they are there. But, since there are some, that handout is from the previous class that you should already have known, but I like to put things in, one place. So here we see now the applications. Now, applications of Charles law are in the hot air balloons. Applications in hot air balloons. Hot air balloons. And what happens in these hot air balloons? So in the hot air balloons, we see that the gas burns. Gas burns here. There's a cylinder here and the gas is burning. And when the gas burns, what happens? The air gets hot. So that's the fire. And again, of course, I can't draw the exact diagram, but just to give you an idea. So the fire burning the gas, or fire heating the gas, burning or heating the gas. It's not necessarily like a chemical reaction, but heating the gas. Okay, so anyways, so when the gases, when they get heated, or when the temperature of the gas increases, the kinetic energy increases of the particles, the collisions of the particles increase. The collisions of the particles increase. That means they are going to push each other. So the pressure increases. Now these gas particles begin to strike the walls of the container. In this, the container is what? It's the balloon. The container is the balloon. Okay, the container is the balloon. All right, so the pressure increases because of the collisions. That is what pressure is. And with that, the volume increases. Okay, now keep this is also in one thing, that when the temperature increases, the density of the gas decreases. So density decreases. When the density decreases means that the gases become lighter at higher temperatures. So as you increase the temperature, the gas is lighter, it's expanding, it's blowing, and the balloon begins to move up. Okay, so that's the whole technology behind this. Now let's look at the learning check problems. So learning check problem. So this is problem 9.6. Okay, a sample of oxygen gas. Okay, a sample of, what is that? A sample milliliters, 30 degrees Celsius. What volume will it occupy at -70? The same pressure. Okay, a sample of oxygen gas, sample of oxygen gas, okay, occupies, the volume given is 32.2 milliliters. Okay, temperature is 30 degrees Celsius. Pressure is 452 torr. And they're saying what volume will it occupy? So this is V1, T1. What volume will it occupy? So we are looking at V2. Okay, what volume? So obviously they haven't said in liters, but let's see, the volume will it occupy at negative. So the temperature given is -70 degrees Celsius. And if the pressure is the same, so pressure is constant. So even though they have mentioned that the pressure value is there, but pressure is not changing. Okay, it's not changing. It's the same in both the scenarios. Therefore, it's constant. So now we are going to do our problem solving here. So here we have V1 over T1 is equal to V2 over T2. So we need to find V2. Okay, so V1 over T1 times T2 is equal to V2 over T2 times T2. So why do we multiply and multiply by T2 on both sides? Because T2 is dividing here, and this is the only way it can get rid of it. So now becomes the equation V1 over T1 is equal to, sorry, V1 over T1 times T2 is equal to V2. And now temperature, remember T1 is 30 degrees Celsius. So here's the thing, you can just do it simply. You can remove this. You can just simply, simply use 273. Okay, and that can be, that's fine too. So plus 273. So what do you get here? That's 300 K. T2 is negative. So here you have -70 plus 273, or in other words, 273 minus 70. So what do you get here? 273 minus 70, and that is equal to 203K. Okay, 203K, and the sign will be of a positive big number. So just plug in the numbers now. 32.2 milliliters over T1 is 300 K, multiply by 203 K is equal to V2. So in this way, the K and the K cancel out. So we have 32.2 times 203. And that is equal to 6536.6. Divide that by 300. And you get 21.78 milliliters. Okay, so that is the 21.6 they are giving you, which is fine because we eliminated that, 273.15. So even if it's in that range, so that's the answer. Okay, so that's the volume of V2 volume. Okay, now let's look at the third one, which is the Gay-Lussac law. So Gay-Lussac, that's, oh, wait 1 second. Okay, let's do this on this one also. There's another study check, 9 study check. 9.7. Okay, here, what is the volume of a sample of ethene? Ethene is a name of a gas at 467 K, 467 K. Okay, 467 K and 1.1 ATM. So this is the temperature, and pressure is 1.1 ATM. Okay, if it occupies 405 milliliters at, that's the volume, at 298 K. So temperature is 298 K and 1.1 ATM. So again, they have given you the value of the pressure. The pressure is not changing. Pressure is the same on both the sides. So we are given the 467K is T1. One second. What is the volume of the sample of ethene at 467? So 467, okay, T1, and we need to find the, I'm going to now erase this. We need to find the volume V1. Okay, and here, K and 1, if it occupies 405 milliliters, this is V2 at 298 K, T2. Okay, so these two are given. So V1 over T1 is equal to V2 over T2. So we need to find the V1. So V1 times T1 over, or in other words, V1 over T1 is equal to V2 over T2 times T1. So this allows you to get rid of T1 from both the sides. So now we are going to put, so this becomes V1 is equal to V2 over T2 times T1. Okay, so V1 is equal to, V2 is 405 milliliters over T2 is 298 K times 467 K. Okay, so here they already did the conversion to K, so you were good with that. So here you have 405 times 467, 405 times 467 divide by 298, and you get 634.68. 634.68 milliliters. Okay, and your book is giving you 635 milliliters. So this is also okay. All right, so that's the answer for these. Next is next comes the Gaelic Law. Now, I don't know why, I'm pretty sure there's a reason for it. They are calling this Edmonton's law, and I don't know why they call it. It's more popular as a Gaelic law. So, oh yeah, the other name is that. Okay, because of this, the pressure of the given, what is it? Guglielmo Edmonton were the first to empirically establish the relationship between pressure and temperature of a gas, and Joseph Louis Gay-Lussac determined the relationship more precisely. Okay, so Gay-Lussac and Edmonton, both of them are like the scientists, A-M-O-N-T-O-N, Edmonton's law. Okay, so both of these guys worked on studying the relationship of pressure and temperature, keeping the volume constant. Okay, so keeping the volume constant. So now Edmonton did the work earlier, but Gay-Lussac did it more precisely. So it's, they're still giving respect to Edmonton for the work that he, pioneered. Okay, so now we have here the Gay-Lussac's, what did he do? So here's this very interesting experiment setup. So these are made up of sealed containers. These are very sealed containers, and In these sealed containers, obviously this is the way, and then there is a regulator here. And this regulator reads the pressure. So pressure, this is called, that is why pressure regulator. It reads how much is the pressure. Okay, now inside is the gas. So just keep this in mind, that if you increase the temperature, the pressure will increase. So all those things are going to apply. So let's get this. Okay, so here we have, okay, first, and let's just do one more. Okay, so we have the three scenarios. One is you have the same gas. The same gas is in a sealed container, which is like made of steel, sealed inside. You put this gas in a heated container or in a hot bath. Okay, so when this gas is in a hot bath, it gets heated up. Note down the temperature of this gas. Note down the temperature reading. So this is going to read the temperature. All of the temperature readings are going to be there. And let's just put this here. This is a steel container. Otherwise, these gases are going to explode if you just put them in just regular containers. So that's why. So here, as the temperature is increasing, we notice the pressure increases. And then different pressure and temperature readings you can take like this. Okay, next you remove this, cool it, and you bring it to a room temperature. Just kind of room temperature, normal. That is why I have it green. Okay, and here then you note down the temperature readings. So what does it reads? What as a pressure regulator is going to read the pressure. And the pressure can be in ATM, can be in PSI, can be in bars, doesn't matter. We don't care. We can always convert, right, the units. But as far as we understand the relationship here also, that when the temperature came down, the pressure also began to come down. And next, you want to check also what happens if you put this in a very cold container. So here you put it like in a full of ice, or maybe dry ice can take the temperature down to -72 or 75 degrees Celsius. So here you have this degree Celsius reading at a very, very low temperature. And here again, we see when the temperature comes down very, very low, very, very low, very, very low, then the pressure also reduces. Okay, so all these pressure readings you're getting from here and the temperature readings from the thermometer. So now you see these relationships that, first of all, why? Back to square one. Why? When the temperature increases, the kinetic energy is going to increase. The collisions in the particles increase. And these collisions lead to increase in pressure. And the volume it's because it's a steel container. Therefore, the steel container keeps the volume constant. The gases cannot escape. It's not like a balloon. So it's very rock solid. So whatever the gases have volume, that is what it is. So when the pressure increases, then that can, even lead to explosion if you continue. So that's like the things, it happens in pressure cookers. Same story. Pressure cookers can explode, so anyways, so what we see here now, that as the relationship, so the relationship of pressure is directly proportional to temperature. So it's a direct relationship, It's a direct relationship. So when we talk about direct relationship, what does that mean? That when the temperature is increasing, the pressure is increasing. When the temperature goes down, the pressure goes down. And how do you express this in a formula? P1 over T1 is equal to P2 over T2. All right. So graph looks the same. Pressure in ATM, temperature in Kelvin. Because of the, variations in the temperature. So here we see that as the pressure increases, as the temperature increases, the pressure also increases. So it's a graph, and in the graph, you can always find the unknown. If you know some of the knowns from the slope, you can just find the unknowns. Okay. Now, where is the application of this law? Application of this law is in the, like, for example, car tires. So they say that during the summer, okay, during the summer, you should not fill the car tires to the max allowed. So summers, keep the pressure, the pressure in the car tires less. Keep or fill less air, basically. Just a little bit less air. Fill lesser air. Okay, because the temperature is going to increase, the pressure inside the tires is going to increase, so the tires are going to expand on their own. So that is why you don't want the tires to explode. So lesser air than, what do you call this? Then, like specified pressure. So that's what it is. So, but in the winters, it's opposite. In the winters, because lesser air in the summer, the air expands. When the air gets heated up, the volume increases, and then the pressure also increases. So when it's expanding, that means the volume is increasing. And so that leads to the increase in pressure also. But during the winters, what happens? Winters, the air compresses. So therefore, you should always fill a little bit more air than the desired or allocated amount. So because in winters, what's happening? Temperature goes down. When the air compresses, what happens? The volume goes down. And when the volume goes down, the pressure also goes down. Okay, so here the tire, it deflates, rather. That's the right word. It deflates. It becomes like a little less. So you should fill more air, especially if you're going in the winter weathers, up in the snow. So tire inflates. And here the tire deflates. Okay. Now let's do this problem that relates to the pressure and the temperature. So learning check. 9.5. 9.5. Okay. A sample of nitrogen gas. So here you're given nitrogen gas occupies, the volume given is 45.0 milliliters. Okay. At 27 degrees Celsius, temperature is 27 degrees Celsius and 600 torr. Pressure given is 600 torr. Okay. What pressure? So now we need to find this other pressure. What pressure? And obviously this is going to be in torr. What pressure will it have if cooled to negative 73? So here the temperature is negative 73 degrees Celsius, while the volume remains constant. So the volume is 45.0 ml. So not changing. So that is constant. The meaning of constant means not changing. Okay. Okay. So now we are few things we're going to do. Convert the temperature to Kelvin. Okay. Convert these to Kelvin. So put this here. Just give me 1 minute. Let's just do this here. Okay. So here we have 27 plus 273 and here plus 273. And so here we get, once again, 300 K, and this one is 273 minus 73. Okay, so that would be 200. 200 K. Okay. So P1 over T1 is equal to P2 over T2. And here we have, this is T1, P1, T2, P2. Okay. So we need to find P2. So what do? We are going to take P1 over T1 times T2 is equal to P2 over T2 times T2. So here the T2 and T2 cancel out. So we are left with just P2 is equal to P1 over T1 times T2. So now just put the numbers. So P2 is equal to P1 is 600 torr, okay, over T1. T1 is 300 K times T2 is 200 K. All right. So here K and K cancel out. So 600 times 200 divided by 300. Let's do this. 600 times 200 divided by 300 and you get 400. So this is 400 torr. That's the value of the next pressure. Okay. All right. So we covered these three main laws and then comes the combined gas law. Let's see if you guys have that. Volume and pressure. Avogadro's. Okay, so you guys don't have the combined gas law. We can leave that, but basically combined gas law, I'm still going to put it here. Combined gas law. Now, what is that combined gas law? Combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. So we see here that pressure, have to be the same on both the sides. So ATMs or millimeters of mercury. So just make sure, or torr, they like to use torr a lot in this book. Torr is also fine. Commonly, these are used. Volume is always in liters, but your book is using so much milliliters, so it's fine, if that is what it is. But milliliters have to be converted to liters. And we already talked about it, that 1 liter over 1000 milliliters, that's the conversion factor. You will multiply that to get to liters. Temperature, always in Kelvin, always. So whatever degree Celsius is given, you add 273 to it, and that's going to give you the Kelvin. Okay, so these conversion, whatever other conversion factors here are, so look at the equalities, equalities, the pressure equalities, noted above. So you will have to make those conversions. Okay. All right. Now here's something very interesting happened. And that is that somebody got really, really upset. And that was Avogadro. Avogadro said that, you guys are very smart, fine, talking about pressure, talking about volume, talking about, these, this is 4, about these gases, and that's 5, about these gases. And he said that, he was not convinced. Why? Because interesting thing is, which we all understand, is the problem with the volume of the gases. And he made actually fun of them. He said, like, you guys are talking about volume. I mean, the gases don't even have a very specific volume, because volume of gases is indefinite. Gases take the shape of the container. Gases take the volumes of the container. And gases, their volume is indefinite because gases love to expand. No matter what you do, whatever container you put the gas in, eventually it finds a little small hole somewhere and it just leaks out from that hole. So they love to expand, right? And they hate to be compressed. That's the nature of the gases. And because of that, the gases can easily, move from the, okay, there's some, I'm sorry, some of you guys had asked me questions. So Akwi is asking, you said when temperature increases, the volume increases. However, you said put a bottle in the freezer. Why does it expand? Okay, Akwi, that's a good question. I'll explain that to you later. That actually relates to hydrogen bonding in water molecules. So we will talk about this piece about hydrogen bonding in the next chapter when we talk about liquids. Okay, so what you are talking about here is liquid water, but we are discussing here gases. Okay, so keep that state of matter in mind. Okay, so we are just looking at the gases. Okay, next is shouldn't T1 be 303K? Which one was that? 303K, which one? I think it was one of the previous ones. 303, which one? Just to clarify, why do we need to convert to Kelvin again? Okay, so Chelsea, shouldn't T, so I don't know which question you're talking about here. Are you talking about this one? 273 minus 70 should be 203 and not 303.
No,
Okay.
I was talking about example 9.6. You added the T1? No, if you go down more.
Okay.
You skipped it. It's a little bit up. It's in the blue. You did 30 plus 273, but then you put equals 300. It's 9.6, that example.
9.6. Okay, let's see. 9.6.
Yeah, T1, you put 30 plus 273 equals 300. Isn't it 303?
Oh, yeah, it would be 303. Oh, yeah. So that would be 303. You're right about that. So 30 plus 273 is, did I put it? Oh, yeah, this is 37. This is okay. So let's just put it in red. So this is 303. So this should be also 303. And this comes out to be 21.78. And that is 9.6. 9.6 is 21.78. Okay, yeah, because of that, this messed up. So the actual answer is 21.6 milliliters. Okay, so just fix that. Okay, thank you, Chelsea. All right, so Heath has a question. Why do we need to convert to Kelvin again? Because Kelvin has a wider range also. And the second thing is that when the value of R that we use, the value of R, that has a K in it, Kelvin. The temperature is in Kelvin there. So it's just just the range in which you can test this. Because remember that these gases, they have tested it at very high temperatures and very low temperatures. So the absolute zero is 0K when all motion stops, basically. So we want to go to that level, 0K, so that's why the 0 degrees Celsius is just the room temperature when the ice is, freezing. So that's what it is. Okay, next is, yeah, K is more precise, exactly. Okay, so that's good. Okay, now let's look at the Avogadro. So Avogadro was upset at these boys. Why? Because he said, you guys are talking about volume of the gases, and this volume is not certain for the gases at all. Gases just take the gases, gases take the volume of the containers. All right, the gases take the volume of the containers. So because of that, this is a problem now. it's fine. We understand. I mean, some gas has to be put in a container, and that is a syringe. And like we can see, like, okay, we have a certain amount of gas there, but he wasn't convinced. Still, he wasn't convinced. So he said, we should know exactly how many particles of gases are we working with. So we know that 1 mole of anything, and in this case, the gas, is equal to 6.022 into 10 to the power 23 particles. And these particles can be atoms or it can be molecules. So it's 1 mole. So at least 1 mole contains these many atoms or molecules, whatever the gas is. And then that is equal to the molar mass of the gas, or whatever. So here's what he did. He said, okay, let's do this. He took these containers, round bottom flasks, okay, and these can be sealed, and these are what we use in the labs. These can be sealed. Okay, so let me just get a few of these. So copy, paste. This one keeps moving. Okay. This one just keeps moving up anyway, so we just need to move further. Okay, so these are 4 gases we are taking. Just take 4 gases we are going to take. One of them, and you guys are going to quickly add the, get the molecular weight. Okay, one of them is carbon dioxide, one of them is chlorine, one of them is xenon, and then one of them is, let's say, ammonia, NH3. Okay, so the molar mass of carbon dioxide is, I think, 44 grams per mole. Chlorine is 70 grams per mole. Ammonia is 17 grams per mole. And xenon is, how much is xenon? Xenon, I don't know. You guys know xenon? What is the weight of xenon? Get the weight of the xenon. 131.3. So 131 grams per mole. So very heavy gas, xenon, right? So these gases, carbon dioxide, chlorine, and ammonia, these are atomic gases, whereas this one is these are molecular gases, whereas xenon is an atomic gases. So keep that in mind. But the molar masses, tell you that this is the 1 mole of the gas. So that is the molar mass, and equal to the molar mass, they took the weights. So 44 grams of carbon dioxide, 70 grams of chlorine, 17 grams of ammonia, and 131 grams of xenon. So that is equal to 1 mole, 1 mole of each of these gas. 1 mole of each gas. And this 1 mole of each gas was placed. The weights are different, that's fine. But at least we came to know that we are dealing with the same number of particles. Each of these gases contain 6.022 into 10 to the power 23 particles. Okay, so the first 3 are molecules, and the last one is the atoms. Regardless, the same particles we are dealing with. Okay, here's a problem. You take this gas, 1 mole of each of these gas, you put them in a tube, they will take the volume of the tube. You put them in a syringe, they take the volume of a syringe. You put them in a cylinder, they take the volume of the cylinder. You put them in a flask, 250 ml flask, they take the weight of the flask. You see, so the volume keeps fluctuating. Never on this earth you can get the volume of a gas. Impossible. If it is in a gaseous state, if the matter is in a gaseous state, impossible that you're going to get the the volume. So then what do we do? Then we have to bring about a transformation. At least we are good with one thing, that we know how many particles are we dealing with, exact number of particles. That is a good part. Okay. Now, what he did was he said, okay, at least we know how many particles we are dealing with. The only other thing you're going to do is you cool them. You cool these gases. So when you cool them, what is going to happen? When you cool a gas, what happens? When you cool it, what happens? The gas converts to liquid. Yeah, it slows down. And then eventually condensation occurs. And you keep cooling it, and then all of the gas is going to convert to liquid. So now we have some liquid that we can work with. Each of these gases are now in the liquefied form. Okay, so what he did was he took a graduated cylinder. You guys have seen it in the labs, and I'm so glad that you guys are actually, you took this class and you at least, got a chance to work in the lab. So you can understand now science better. Otherwise, there's no point of taking science if you don't have the labs done properly. So you have a good hands of experience. So here is the graduated cylinder. Graduated cylinder. So that's fine. You have a graduated cylinder, and now you transfer each of these gases in this graduated cylinder. You transfer them, and you transfer, not like one by one, not all of them mixed together, but one at a time. Once you put and see what is the volume. What is the volume of this? So it comes out for carbon dioxide, 22.4 liters. For chlorine, 22.4 liters. For ammonia, 22.4 liters. For xenon, 22.4 liters. So 22.4 liters is the standard for 1 mole of each of these gases. 1 mole of the gas has the same volume. Okay, so 1 mole of gas, which contains 6.022 into 10 to the power 23 particles, all of them are occupying 22.4 liters volume. Remarkable discovery, right? Amazing. Now 22.4 liters, then this becomes this is also called a molar volume. This is called molar volume. And then that becomes a standard. Molar volume is 22.4 liters per mole. Per mole means 1 mole. 1 mole of a gas. Okay. Now, simple common sense after that, that as you increase the number of moles, yeah, the volume will increase. As you decrease the number of moles, the volume will decrease. And so there is a direct relationship between the volume and the number of moles. And we have the formula V2 V1 over N1 is V2 over N2. And in this case, the graph, again, if you do not know the number of moles, like of say unknown, then as the volume, this is volume in liters, and this is the moles, then as the moles increase, the volume also increases. Okay, so that is the Avogadro's law, and there is no learning check here, but oh, they have a combined gas law later on. They've given you, anyways. Okay, so we don't have a, okay, so this whole information was then collected, and they said, okay, fine, we need to bring in the moles in our formulas, then it doesn't make sense. So they said, okay, how can we now? They can't change a lot of things, they couldn't change. So they said, okay, we will have to make an ideal gas law. Ideal, we know, because gases are gases that we are dealing with on this earth. They go through the change of phase. So because of that, they're not gases anymore. After some time, the gas laws won't apply. So ideal gas, will not go through the change of phase. So as you keep increasing the temperature to millions even, the volume will continue to increase. That's mathematically only possible. Okay, so what is the formula then? Formula is PV is equal to N or T. Now note down here, when the pressure is measured in ATM, the value of R is 0.08206 liters times ATM per mole K. Kelvin. When the pressure is in millimeters of mercury, then the value of R is 62.4 liters times millimeters of mercury per mole K. Okay, these two things. Then the volume has to be in liters. Anytime you're using this ideal gas law, volume in liters, temperature in Kelvin. Okay, so make those conversions we already discussed. And N is the moles. So if you are given something in grams, you need to always convert it to moles using the molar mass. Okay, using the molar mass. And that will be convert to moles. Kelvin, as we talked about, degrees Celsius plus 273 Kelvin. And then liters, we talked about milliliters converted to liters using 1 liter over 1000 milliliters. This thing. Okay. So now let's look at 9.9. Learning check. Learning check. 9.9. Okay, here, calculate the pressure in bar. Okay, pressure, they want it in bar. Okay, calculate the pressure in bar of 2. So the number of moles given is 2,520 moles of hydrogen gas. So this is the hydrogen gas. The moles is 2,520 is given. Hydrogen gas stored at the temperature is 27 degrees Celsius. Okay, in the volume is 180 liters, tank of a modern hydrogen powered car. Okay, now here we have the pressure in bar. So PV is equal to nRT. Okay, so in this case, we will have to use the value of R as 0.08206 liter atmosphere per mole K. Why? Because we are going to first find the pressure in atmosphere. Okay, then later convert the ATM to bar. And ATM to bar, back to, initial thing that I already wrote for you here. 1 ATM is equal to, okay, no direct conversion of ATM to bar, but Pascal. So convert ATM to Pascal and Pascal to bar. So 1 ATM is 101,325 Pascal. 1 ATM is 1 ATM is equal to 101,325 pascals, and that 101,325 pascals, and then pascals is how many pascals? 100,000 pascals is 1 bar. 100,000 pascals is 1 bar. Okay. 1 bar is equal to 100,000 pascals. So we'll use this. Okay, so first find the pressure. So pressure is equal to N R T over V. Okay, so here, let's do the temperature also. So 273 273 plus, this is, okay, so 10, 10, 300 K. And volume is already, so 2520 times, so 0.08206 liter atmosphere per mole K times temperature is 300 K over the volume is 180 liters, 180 liters. And remember, this is moles. So we see here, moles and moles cancel out, liters and liters cancel out, K and K cancel, and you're just left with ATM. So let's do this, 2520 times 0.08206 times 300 is equal to 62037, 62,037.36 divide by 180. Divide by 180. 344.65. 344.65 ATM. Okay, so this is the pressure. Okay, next is we are going to look at the pressure is convert the ATM to bar. So as we talked about, first you take the ATM, convert to Pascal. So 344.65 ATM times 101,325 pascals, divide that by the ATM, 1 ATM. And let's do it here only. And then we have 1 bar over 100,000 pascals. Okay, so let's do this. 344 times 101,325 divide by 100,000, and you get 349.21. So pressure is equal to 349.21 bar, and your book is giving you 350 bar, which is fine. You know, I may have, because some certain things in the calculation, especially after the decimal point. So, okay. So that's one thing. And then there is a combined gas law. So then comes the, okay, I want to just finish this last piece, which is combined gas law also. Let's do that. This is the study check. Now they're doing this combined gas law in the end. I don't get that. Combined gas law is supposed to be done here. So this relates to the study check 9.10. Okay, so let's do this. So 6, 7. So this is, sorry, the learning check, sorry. 9.10, and this is combined gas law. Okay, so here you are given a sample of ammonia. So NH3 gas is found to occupy, the volume given is 0.250 liters. Under the laboratory conditions, temperature is 27 degrees Celsius and pressure given is 0.850 ATM. Find the volume of this sample. So find the volume. So that's V1, T1, P1, V2. Find the volume of the sample at temperature T2 is equal to 0 degrees Celsius and pressure is P2 is 1 atm. Okay, so the formula is P1 V1 over T1 is equal to P2 V2 over T2. So we need to find V2. So what do we do? So here we have P1 V1 over T1 times T2 over P2 is equal to V2. So you guys know the algebraic conversions. So now we are going to just plug in the numbers, but we need to add 273 here, and this becomes 300K, and this one 0 plus 273, and this becomes 273K. Okay, so next is just put in the numbers here. So P1 is 0.850 atm times V1 is 0.250 liters over T1 is 300K times T2 is 273K over P2. P2 is 1.00 atm. So here we see that this is equal to. So we see here that K and K cancel out, ATM and ATM cancel out, and you're just left with the units of. So just do the math now. 0.850 times 0.250 times 273 is equal to 58.01 divided by 300. Oh, did I do this right? 273 times 0.250 times 0.850, and you get 58.01. Divide that by 300, and you get 0.193 liters. Okay, 0.19 liters translates into 19, I think it's 193 milliliters, 193 milliliters. Okay, so that's the thing. And now comes the absolute last piece, which is this 8. And that is, here is the standard temperature and pressure. So when we talk about standard, so standard is like, you know, when like everything is in reference. So temperature is either 0 degrees Celsius is considered standard when at a temperature where the ice freezes, or 273 in the terms of, you know, Kelvin. Pressure is always either it's 1 atm, but we also sometimes consider, because 1 atm is equal to 760 millimeters of mercury. Okay, so these are both standards. Then comes the N is equal to 1 mole is considered standard. And then comes the volume, which is 22.4 liters. Okay, so that's the standard temperature pressure conditions. So you have to read the question. If the question is asking you like at standard temperature conditions, so use, so I'm going to just put here, note, if question indicates STP, you can never go wrong, then use the above values. Okay, guys, so it's a long, it's a big chapter. Okay, so 9.6, I have to do the stoichiometry, density, molar mass, finding the pressure, all that stuff, mixed pressure of the mixture of gases, the collection over water, and the Avogadro's law. Now they're coming back to Avogadro's law. Just the way this whole chapter is very vaguely designed. Anyways, evolution, effusion, all that. So the thing is that you guys have a holiday on this Tuesday, and we have after this, let's just see, just let me stop recording.